I had to take notes because Pravin is a good friend and he was my teacher for many years when I was at the University of Illinois in Chicago. But his CV is convoluted. The man couldn't make up his mind to do anything and not change after a little while. I'm not sure if it's ADHD or what was going on. Yes. So Pravin actually started as an electrical engineer. He decided to start studying quantum electronics at Johns Hopkins. Then he went for a job at IBM for a couple of years, decided that that wasn't enough, so he went to Brown to study particle physics. So he did that for a while, but then he decided that wasn't enough, so he decided to start studying brains of invertebrates for a couple of years. Couldn't figure out a career path that really was something that he could stick on, and tried a couple of other careers, and then finally he decided he would become a surgeon. So first he went to the Mayo Clinic, became a general surgeon there. Then he decided that maybe because he was an engineer and mechanics were of his liking, he would become a hand surgeon. So he decided to become a hand and microsurgeon, trained as such at the University of Chicago, stuck around Chicago for a little bit because he loved the winters, and decided to go to Northwestern and study craniofacial surgery and finally studied craniofacial surgery here at UCLA in California, and returned to Chicago and has been the chief of craniofacial surgery and pediatric plastic surgery there, both at the University of Illinois as well as at Shriners Hospitals for Children for a little over 20 years now, and has a wealth of experience. Last night he gave a lecture on pediatric plastic surgery where he put most of the audience in awe with a couple of really fantastic reconstructions, and today he's going to talk to us about craniofacial surgery. Thank you, Pravin.
Clearly, I'm a guy who couldn't live in one place for a while till I got stuck in Chicago and finally had to make some money. Well, anyway, my parents always wondered what I was really going to do. Dr. Farmer made a great comment earlier about ulcer surgeons. I trained in that era. The Bill Ross 1, the 2, the Roux Y loops, all that. And of course, the Metadine came along, and there's just no way I could go back and do general surgery. Things just changed with time and evolved with time. And I tried to put together a lecture that would be at least interest to all of us, I think. Something in it for all of us. So this is not a real lecture about anything, really. Just about surgery, I think, in general, that I could be applicable, whether you're talking about craniofacial surgery or general surgery or any other specialty in terms of, my children live in a digital age, but like many of you, or at least some of you grew up in an analog world. And except for the residents who, grew up in a totally different world of digital, like my kids. But, as a surgeon, I'm part of that evolution from an analog head to a digital head. And a lot has happened in the past quarter of a century, and that's what this talk is really about. So this is really a tale about craniofacial surgery, but it's really a story about, remarkable surgeons, and I put Paul Tessie and Hugo Obegazer, and you really could put other surgeons in the general surgical field in there as well, too. It's also about a Nobel laureate, Gottfried Hansfeld, and a band called the Beatles, which is not a likely group of individuals to appear in the same story or the same tale. So let me see if I can make this connect. So, using this quote by Steve Jobs, it's been overused a bit, but it works apt for this lecture. You can't connect the dots looking forward. You can only connect them looking backwards. So let me start by looking backwards a little bit. As Perko told you, I've been in practice now, in one place for the past 2 decades now. So I want to turn back the clock by, let's say, 20 years. When I started out as a young surgeon, I picked a number of cases from that first year that I tackled as a young surgeon. And this is a child who's born with a fused skull joint. I had a fair number of cases by then. But for me, this was an outlier when you really look at the head-shaped deformity. So what did I do to prepare for this surgery? Nothing really. I just had nothing to work with back then in 1994. You have to think about what things were back in 94 compared to what you have available today. So basically, I really didn't do much for preparing for surgery. You have to remember that CT images in 1994 were 2D slices, and they were on film. If anybody sees light boxes anymore, they've been ripped out of most hospitals, I think. So I had to create the 3D images of the skull by stacking those slices in my head like this. I had this analog brain. I was constantly trying to stack these slices that I would see. And the problem with that my analog brain had was I could imagine a variety of different possibilities, none of which probably had any bearing to reality, actually. In other words, the CT showed me the problem, but but not the surgical solution. I really couldn't visualize it three-dimensionally. Just wasn't used to looking at slices like that. And our brains really were not able to reconstruct it as accurately as we needed to be able to do the surgery. So this was really a cut and reassemble job. It was basically, you did this on the fly, and like most of my cases in that era, we basically took apart the skull, took the skull top off here. This is the front of the head, back of the head. Here we go, front of the head, back of the head. And the skull is pretty much all off, and basically you're looking at the dura here, and then you just have to, sort of figure out a way to piece it back together again. And so, this was basically you cut and reassemble as a technique. You really didn't have any real good guides or plans to put it back together again. So here she is from that first single operation. I planned it as a two-stage procedure, because I didn't think I could get it right the first time. But the mother said that was good enough. So here she is in 2000, and here she is in what do I have her? Here she is in 2006. So again, with a single operation, I think I did a fairly good job, but really I think this was just beginner's luck back then, This is another case I did in 1994. Again, this is my first year in practice. This is not your typical rhinoplasty procedure here. Two halves of the face just didn't come completely together again. So the question I need to answer was, how far should the eyes be apart? So my extent of planning, I did some planning, and the answer is basically you look at an artist's textbook on how to draw, and you realize, oh, your nose width should be about just one eye apart, So that's what it should look like. So that's about my surgical planning that went on. So in the OR, most of the procedure is really done on the table. You're taking off the nasal bone, all that excess bone, then you're going to trim out the ethmoids, and then basically you get your fingers in there somehow and translocate the orbits like that. So again, this is really on the table surgery, planning surgery to get this kind of an outcome. Again, beginner's luck, I think. So this is another case I did in 1994. The eyes are in the right place, you got to remember that, but everything else is in the wrong place here. All the bones are really in the wrong place. The eyes are connected to the brain, can't move the eyeballs, but you can move all the bones around it. So despite a clinical exam and staring at the CT, how far to advance the face was really an on-the-table surgical decision for me. And here he is after monoblock, facial advancement, and Lefort 1 BSSO. You don't have to worry about the technique, but you just have to see this is the before and after, and there was hardly any real planning that went on. There was far more planning or treatment planning in the typical this is called an orthognathic case where you're straightening out the jaw here. There's a lot more planning for the simple cases like this, not for the really complex cases. And the way we planned these cases out was, you took photographs, sort of block diagram, what I thought was wrong. You had x-rays, two-dimensional x-rays, which you could plan off. You did some tracings, you got some numbers, these are normative data, and then basically you make this model surgery with the dental models, and then you make a jig out of this, and the jig is right here, over there, splint fabric, and you take that to the operating room, and that sort of guides your surgical planning. So for the easier cases like this, I had something to work with, not for the tough cases. And so here she is in the operating table where I took off this much amount of bone from the upper jaw here. Everything's hanging off the back portion of the maxilla, and then you section the back portion of the maxilla, and then bring the jaw up, bring the lower jaw forward, and do a chin for her. And so here she is before and after the surgery. So again, this is really not a complicated case. It has a lot of steps to it, but not as complex as the other cases. And here I had a lot more planning that I could do with these cases. So I had cases like this. This is not an uncommon case in teenagers. A lot of them really will have some degree of facial asymmetry because one side of the jaw grows faster than the other side of the jaw. And after you section the bones, where do you put the pieces? Again, once you cut them, the whole problem is where do you put all the pieces in there? So this becomes a problem in Euclidean geometry, right? You have a three-dimensional space. Here are the bones, 1, 2, and 3, and it becomes a surgeon's puzzle, right? And each piece, these are 3 pieces of bones that I can reposition in space, and each piece has 6 degrees of freedom, right? 3 translation, 3 rotation, so that's 6 degrees. So where do you put this in space has always been a problem for the surgeon in our specialty. And of course, what we used back then is we used two-dimensional x-rays. We really didn't use 3D. We didn't get CT scans back then. You got to think about 1995. It's way too much radiation. Really wasn't applicable. We just got 2D x-rays, and somehow our brains had to make orthogonal components of that and use that for surgical planning. So in the operating room, it sometimes took a bit of time to get things right. You put it together, didn't like it, reposition all the pieces, and eventually you get things right. So the operations took longer to get them in the right position here. and minutes would just tick away in the OR, and you pretty much get lost in the OR sometimes. So here's the same operation I did. And from here it looks good. I got it right. But if you really look at it, but most often I got it wrong. Because if you look at the profile view, she just doesn't look right. And it was hard to deal with all these asymmetries, how to put the pieces in a consistent way. And you're a young surgeon trying to get consistent with your outcomes. And this was a bit of a waste of time doing all that model surgery. So these are the more complicated cases that I deal with here, cases like this, and these are even much more challenging to do. So, taking things apart is not that difficult, right? But putting things back together again is a bit of a challenge. There are two different tasks. Taking something apart and putting back together again are two different tasks, and the hardest task, of course, is putting things back together again. So getting good, I think, getting consistent good surgical result means becoming more efficient, technical efficiency in the OR, and then translating that to a surgical plan. The problem is that for most of the complex cases that we didn't have a good architect's blueprint to work from. And it's just like builders, right? You can build a house without an architect, right? But just like builders, like surgeons, you can find yourselves in the OR having to solve construction problems that you didn't plan for. But if you have an architect's plan before you walk into the OR, you at least can anticipate some of those problems. And back in 1994, 1995, if you think about the mid-1990s, we really didn't have a good way of coming with these plans here. So a lot of it was basically surgery on the fly. So, how did surgeons navigate? Well, just like, everybody else, if you remember, my boy's 13, I showed him a map. He said, what's that? They're used to the iPhone to navigate. And he was really fascinated by these old paper maps I had. He had those things outside. But the same thing, if you think about 1994, here I am driving to Michigan to go to the University of Michigan to get grand rounds from Chicago, and I got lost, And back then, you take out the map, and instead of talking on the phone as you're driving, you can see what I'm doing. I'm driving with the map open, right? Which you shouldn't be doing either also. But, I think the thing is, it's just that when you drive to go from point A to point B, you'll get lost the first time. You come back and you do get, and each time you go from point A to point B, you get better at it, you get more experience, and eventually you can close your eyes and get from point A to point B, right? That's the same way with surgery, I think, right? As you're a new surgeon trying to figure it out, the first time it takes longer to figure out to go from point A to point B. Same set of problems that we have to solve mentally. How do you get consistent? How do you find that path so it just becomes automatic, so it becomes hardwired in your brain to go from point A to point B, whether you're driving a car or whether you're in the OR. So you're not stuck, lost in the operating table, right, with the belly open or with the skull open. So what I learned early on was that whatever quantitative surgical planning that was available was only for all the easiest of the cases. There was no real planning. Most of it happened on the operating table, cut-as-you-go approach, and the outcome was based on experience and luck. And not only did I not have a clear plan until I got into the operating room, I had the problem of teaching the resident, right? So that was always a challenge for me at the beginning. So, solving such problems is not new, right? A half a century ago, these problems were solved largely by two remarkable surgeons, Hugo Obergaiser and Paul Tessier. They're both remarkable surgeons, and they were solving the same problems that I was solving. So in the case, this is Obergaiser, who sent me these 35mm slides that he digitized and sent them to me years ago from 1972. But here he is operating, reconstructing the jaws on his face. And what did he do? Basically took a photograph, drew outlines, said, that's the face I want. Did some models with the teeth, because you move the teeth with the bones. This is some artist diagram, but you can see the same sort of complexity. And basically executed a fairly good operation outcome in 1972. Again, without a lot of tools, just a couple of x-rays and a photograph, right? This is Paul Tessier in 1978, the University of Illinois. Paul Tessier is a French surgeon from Paris. And Paul Tessier really gets the credit for the quote-unquote, the name of the father of craniofacial surgery, let's say, right? So here he is. This is a complex hyperteleorbitism case, and all he needed was a good examination of the patient, a couple of plain films to have an outcome that looks like this. Now that's a remarkable outcome in 78 to get a result like that from a complex move. So basically, everything was wired in these guys' brains to get these outcomes, So conventional old conventional planning does work. Clearly it works in these guys because they had good analog heads, right? They've been trained, they've got it hardwired, they've done so many surgeries they can actually execute these operations. But you had to be an Obergäser or a Tessier to get results like this. So it worked well if you happened to be an experienced surgeon like Tessier here. You didn't need a road map. The road was well wired in his brain. Then the problem is, how do you transfer all that knowledge to another generation of surgeons? This is young Tony Wolf, another craniofacial surgeon here. How do you transfer him? He just started out as a young attending, and this is some unknown resident at the University of Illinois, right? How do you teach a young surgeon attending to become a better surgeon, and how do you teach the residents? I think that's a fundamental problem we all have, right? So this is my boy and I obviously am, carving here totem poles with him. But I think surgery at its core is a craft. It's one-on-one apprenticeship, really, I think it is. And it's no different than me teaching my little boy how to carve trees. The tools have remained the same for centuries. I think that's the way it is in surgery. It's still an apprenticeship when you look at it that way. It's a very unique specialty to be doing that. So how do I teach my boy how to carve trees? Same thing, how do you teach residents, right? Same problem. So figuring out how to be a better surgeon, I learned early on when I was a second-year general surgery resident at the Mayo Clinic. I was asked to evaluate myself, and you probably can't read this very well. Now, today to evaluate residents, we have all those Likert scales and all those numbers that you fill out. But the Mayo Clinic, back then, it was pretty simple. I was asked to evaluate myself. This is 86, August 15th, 86. I kept this, actually. I've had it folded up in my drawer for many years. I was asked to draw a curve of the surgical abilities among surgeons and mark where I thought I was. And I thought I was being pretty fair, so I put myself right about here. I put myself as an average resident here. And but if you notice, I actually skewed the curve, right? Surgeons always think better than they are, right? So where do you think you're a surgeon? So I think surgeons have a tendency to skew. So Michael Sarr was my evaluator, my attending, and he drew the curve like this, and he said, no, it's a bell-shaped curve, Pravin. Here's where I think you are. Oh, here we go. Here's where I think you are. Well, here's like I'd like to see you someday as a chief, if you can make it that far, right? That was my evaluation. That was it. We shook hands, and okay, done. So, the practical advice I got from Dr. Sarr was that the painful truth is that surgeons, including Mayo surgeons, live on the bell curve. And Pravin, the question is, where will you be when you're chief in a decade from that, right? Even surgeons, all surgeons live on a bell curve one way or another. And I think I never forgot that when Michael told me that. So, you're always somewhere in that curve. And it's a question, where will you be relative to everyone else? So the question then comes to be, well, where would one put remarkable surgeons, let's say Paul Tessier and a select group of other surgeons, no matter what specialty, on this bell curve? Well, you'd have to extend the bell curve, right? So Tessier and Obergäsers were outliers, right? Outlier person or thing situated away or detached from the main body of the system. In statistics, an outlier is an observation that's numerically distant from the rest of the data, right? So we have a group of surgeons out here, Halstead. Anyone in general surgery you can think of could fall into this category. And the rest of us are down here somewhere in there, right? So the first question, I think, is, can computers make us better surgeons? Can it shift the bell curve, right? So that some of us can be as good as Tessier and Obergäser. That's the first question. Can all this technology really help us as surgeons? So can it make surgery more, so what you translate that, can you make surgery more precise, more accurate, change the axis for accuracy and precision? And of course our reference would be, let's say, our gold standards for this example is Tessier and Obergäser, right? And the question is, can it have any impact on the training of surgical residents? So that's the second question I'd like to answer today. Two questions I want to get through. So this is Sam Brzezinski, who's an orthodontist, who passed away a number of years ago, but I remember this quote from it. So, why should each case be an experiment in nature? And so why should the operating room be a research lab and the only training ground for our residents? And of course, things are evolving both in your specialty and our specialty as we go towards simulations. And I think it's a big change toward that. So I think surgery is an old craft. The instruments then and now are the same. not much has changed in the instruments if you think about it. Instruments have been optimized, right? There's no point in inventing new instruments like this. You know, those are really optimized instruments. Chisels, hammers, saws, sewing, needle holders, forceps. Those have been optimized. So there's no point in putting more time into that. But the world has changed, right? Surgical instruments haven't changed. The world has changed. This is my slide rule when I started out in college to an electronic calculator, right? How much has changed between the two periods there? This happens to be my Smith Corona that I pounded out my college applications. I still have this, and my kids are really fascinated by this now. Actually, they pound on that thing. So they haven't seen one. Of course, all they know is laptops and iPhones and that sort of stuff. And then, of course, this is what it's evolved to a laptop. Just think of how much has changed between the two. I made so many mistakes on those college applications with the whiteout and all that sort of stuff, right? This is my telephone when I went to Hopkins, actually, and I still use it because sometimes my digital phone line goes out. I still have an analog line. I kept this one phone there. To an iPhone, right? So everything is gone, right? My camera from 1994, 1995, the office phone, the calculator has all been replaced by the iPhone, right? It's amazing what things have changed so much, I think. And even now, when you think about it here, if you think about this, I don't know if you can hear this, but this is a 1960s a commercial. There's an audio to this. I can't hear it, but that's okay. 1960s audio. I grew up in the 1960s, and I remember this, actually. You know, I remember growing up with Dick Tracy. I remember this, and this is actually a transistor two-way walkie-talkie. And the thing is, this is one of the things that drove me into electrical engineering, really, because I saw this as a kid growing up in the 60s, right? It's a race to the moon, right? You remember that, the Apollo missions and all that? And this is what I grew up, and that's why I went into electrical engineering, actually, because that's what I saw in the future. And here I'm back at an old specialty doing surgery, of course. But anyway, things have changed so much. So if you could plan surgery virtually, I use this as a slide. If you could plan surgery virtually, we should have more predictable and consistent results, at least in terms of the technical execution of the plan. The best example I can think of is really designing better bumpers of cars. This is just analogies, just to show you, for collisions, for example. So when BMW wants to design a new bumper or front-end assembly, it doesn't take a brand new BMW each time and run it into the wall, right? It's far too expensive of a product to be constantly destroying it. So what do? Well, they build a 3D virtual world, use engineering techniques, put finite element analysis to it, and then they simulate the crashes. It's far more cost-effective trying out various, different front-end designs virtually, using on a computer, and then fabricating the prototypes, right? That's the way it should be. Now, the question is, can we actually apply it to surgery, right? And you think of how the world has changed, yet for surgeons. The operating room for us, for a long time in plastic surgery, has really remained the same. I was 16 years old in 1975 when the first PC came out, and I had wanted to build that as a kit, right, of the 11th grader at that point in time. And I saved up my money selling newspapers and whatever to spend $400 to build a computer. In 1975, what was Bill Gates doing? He was a second-year college student at Harvard who says, well, you know what? I'm not going to even build this machine. I'm going to write the language. I'm going to write the software so everybody in the world could do this. He was obviously much smarter than I was back then. And of course, he drops out of Harvard, starts a company, and the first company, Microsoft, was actually in Albuquerque. He didn't even actually had the PC. He convinced the owner of the company, listen, I've already written the software for you. He didn't even actually write the software, went down there, cut the deal, and then spent the next 6 months at Harvard writing the software, and then dropped out of Harvard with his friend Paul Allen. And of course, that's Microsoft. So the first company was in Albuquerque. He had foresight. I didn't. Anyway, so is it possible to truly plan the surgery on the computer? And can you simulate surgery as automotive and aeronautical engineers really do? So, if you look at this, you could get 3D pictures, but this is on a 2D screen. I'm putting a tracing paper, and I'm teaching the residents with a grease pencil how to do the surgery. This is no better at them looking at a surgical atlas. This is really not surgical training. Even though I have 3D data, this is really not any real simulation. This is just tracing paper the morning of surgery. So it really wasn't, despite the fact you could get nice 3D images, you really couldn't do anything with that data until you could begin to manipulate that data. Think about that, right? We had 35 millimeter film back then, right? The mid-1990s. You couldn't do anything. You took the photographs, you printed it, you put them in an album. Now, with your phones, You take a picture with your camera. They're digital images. Once you can get the digital data, you can begin to manipulate the data, right? Everybody's like doing filters on their phone, changing to black and white or whatever they're doing. So once you can get that data, the problem is the computers at the turn of the century, right, 1990 to 2000, even though you can get the 3D data, you couldn't do anything with it. It's only when you had enough memory, processing power, and finally we could write the software code to it to be able to manipulate that data. But all that data was still sitting in the CT scan. It just couldn't be unlocked until about the last decade or so. So anyway, these are our 2D camera, which gets replaced by a 3D camera. Our 2D X-ray units, which gets replaced with a low dose radiation 3D CT scan for the face. And now we actually have a digital image of the patient that we can actually work with on the computer. So this is a girl who's born with a cleft lip and palate. So instead of 2D plain films, we have her skeleton in 3D. And now there's so much more information that we have, right? In 3D, there's all sorts of data that we can now do. And what's the beauty of it now, of course, is that we could even begin to manipulate this. So, of course, this is 3D. You're looking on a 2D screen. So if I could give you 3D glasses, this actually looks pretty amazing. You can actually see it and get some sort of perspective. So you can now begin to simulate surgery on the computer, which we couldn't do, in the mid-1990s. So now it becomes just like a cookbook recipe, right? Gives me all the moves, how many degrees, the 6 degrees of freedom that I can do. Now you got to translate that into the operating room. The other thing you could do is, getting back to my collision, there are things we can now see that we couldn't see before until we got into the OR and then got stuck. These were, when we do a rotation of the lower jaw, these are collisions that happen at the osteotomy sites, which we couldn't do before. So instead, you got to remember, we're working through small incisions inside the mouth, so we don't have big incisions outside. And so you're looking through keyholes, and now you can visually see things. You can never get this view, right, in the OR. So how do you transfer something out of the virtual world, the computer, to the real world? Well, how do you take something out of a laptop, right? Here's a Word document. You hook it up to an HP printer or an Epson printer I've got here, right? You just print it out. Same thing. You could just go to Amazon and buy a 3D printer for about $1,000 here. And it's the same concept. You're just printing, whether you're printing paper or printing 3D objects. It's the same thing. In a Word document, it's a .doc file, right? In a 3D object, it's a .stl file. Same concept, nothing more complicated. So now what happens, that jig I showed you earlier, I want to manufacture that jig, which takes me into the OR. That's a 3D printer that we have, and then I just take that to the OR. So you don't have to really know the details, but you can take something virtually in the computer, print it into the physical reality, which is computer-aided design, computer-aided manufacturing. And so you can replace this with this on the computer. Now I'm just going to speed this up a little bit here. So again, same thing. You can make guides here to make these cuts, bony cuts here. These are like virtually designed guides. Same sort of software that the automotive engineers do when they're designing cars. We have the same thing here. So now what happens is you can make these osteotomy guides so even the resident can cut it, right? I just put the marking guide, screw these things, and I can give them the saw without any problem. That's a resin just simply cutting it. It's like a cookie cutter, which I could never do before. The other thing I can now do is, and not many of you work with plates and screws, but I do. But this is a plate design that we virtually designed on the computer. We manufactured it, and then just simply took it to the OR. And I'm just going to skip through this. I think it's just to save time here. But the same concept, I think you get it. You can screw these things in. The saw goes through, cuts it, and then reposition the upper jaw. You put the plates and screws and move it into position here. So let me go through it. So basically that plate just gets repositioned right here and pops into position. So here she is before, and here she is after surgery, 2 years after the braces are off. Again, we didn't do any nose surgery yet on her, a little touch of rhinoplasty, but again, this is all done by virtually planning everything ahead of time. Now, what about something more difficult? This is the true craniofacial cases. Can we apply to this? So here's the problem with these cases. Small volume cases, some of these are very rare. The outcome is really dependent upon the surgeon's experience. There's a steep learning curve, difficulty teaching the surgical residents. It's a technical aspect, cut-as-you-go approach, which I start out with. So let's say you have a kid like this with a fused skull suture because of this asymmetry. And so what happens in the operating room is this. We're using a number 2 pencil here. You give the resident a pencil, and you say, why don't you mark out what you read last night where I should make the cut? So the resident marks it out something like this with their pencil. And I say, oh, that's never going to work. So I say, no, you got to cut here and here. And then the resin, of course, says to me, well, why don't you cut here to here? And I have no answer, because I say, I know my cuts are going to work, your cuts are not going to, and I can't explain why this is not going to work to you. Because why? Because I've been doing this surgery for 20 odd years. I just know that's going to work. So how do you teach that to the resin, right? So it gets back to this problem. How do you take something apart and rebuild it? So here, these are kids with various skull deformities here. And the surgeon's problem is to reverse the direction to a normal skull centrally. So no matter what the deformity is, how do you get back to the normal skull? So a good way to simplify the surgical problem is, we know there's the American version of the football, and then there's the version of the world that the rest of us call footballs too, right? This is a soccer ball, right? So now, let's talk about simplifying the surgery. This is the morphology of footballs. So how do you take a prolate spheroid and convert it to a sphere, right? So basically, if you can operate on a football to convert from one football to another football, it's the same thing as doing a head. So basically, you just have to figure the algorithm. So we need to figure out what that A is and somehow train our heads to do that. And so one simple way is to take an American football, cut it, disassemble it, reassemble it, and that's one algorithm to do that. But if you cut it even finer, you can get a better looking rounder head ball, right? That's basically all skull surgery really is. Simple as that. So basically, it's a very good analogy between the two components here. So here's a patient with a unilateral coronal synostosis. You can see there's a joint here, joints missing on here, and that's why you have the skull asymmetry. And so again, gets back to taking it apart, it's not difficult. Putting it back together, again, it's tough. And so how do you really build it? So a good way to think about it is, it's like a puzzle, right? You have all these puzzle pieces here. How do you put puzzles back together again as kids, right? Well, you work with the perimeter, right? If you know the perimeter, then you put the first set of states in. Got that? And then you have another perimeter, an internal perimeter, right? Then you have these states here. And then you're left with these three states, which I'm sure none of you really know what these states are, right? Because you're from the West Coast, right? Missouri, Kansas, and Nebraska. But you see how you can build the face, right? It's the same concept here. You have to have some algorithm in your head, and that's actually how the codes are written. So what are my perimeters for the skull? I have an orbital perimeter, and I have the frontal contour. So if I get those two perimeters right, then I can put the rest of the puzzle pieces back together again. Same concept. So now on the computer, this is the abnormal skull here. And what you can do is do a mirror image on the computer, which you could never do before, so that's a mirror image. And then we have age match controls, and between the two, you could say this is what our surgical plan is. So this is what the corrected shape should be. Now this is not real, it's a computer-aided design. And then you print it, so now you got computer-aided manufacturing, so it's 3D printed, so this becomes a real piece, and you take that to the OR. Oh, and for the first time, the residents actually have homework assignments, because now on the computer, they can actually play around with this, cut the pieces, move the pieces around to optimize the shape, to which we never had anything before like that. So that's a supraorbital rim off, so that's the orbit, and the frontal bone's off, but just to give you, here's the orbital rim here, lateral orbital wall, here's the nose would have been here, and this is the temporal bone come here. So that's out. This is the shape it should be from the template. This is what it is. And this is a templated piece that I bent, this resorbable plate. And here's after I've reshaped the bone using rongeurs, old-fashioned instruments, you know. So you can look at it from the top down and the bottom up view, but again, you reshape it to the template. And then this is what it looks like. So here's the brain for orientation. Before I flap, eyeball is back in there, eyeball's flipped to that side. And this is the piece that's going in just to show you. And then that's the piece that I, reshaped, put that back in. And now you can get the angulation between right and left correct. So that's the design manufacture piece, and this is the actual reconstructed piece here. And then for the rest of the head, right, you have all these printed patterns, templates here. These are the bone pieces on the back table, the skull pieces. And so this is a lot like, those are the bone elements. So it's a lot like patterns, right, when you do tailoring type work. And then just with the resin came up with this design work, A, B, C, D. Same sort of thing, sort of put it in, reshape it. And here she is, 1 year, 2 years out. But you can see the difference here between the two components of it. And so here's another case 27C that we did. This was from a study that we did here. So again, you could see straightforward operation. So something that was really complicated, I think the residents now have something to work from. So let's apply this to something even more difficult. That's not that complicated. Going back to this kid, which I really think is a hard problem to solve. So this is a child born with Cruzon syndrome, had an operation in Japan, and initially moved to the States, came to see me, and this is what his CT scan looks like. You can see that the eyes look proptotic. They're too far out, right? It's just that his eyes are in the right place, but the bones are all in the wrong place here. So this is the virtual operating theater. Just like the other pieces, you cut it into 3 different segments here, move it into, here on the computer, you're moving these components. Now the question is, where do you put it in space, right? Where do you put it in 3-dimensional space? Well, this is my boy when he was 9 years of age. So when he was 9 years old, he went to see the orthodontist, and the orthodontist got a cone beam CT scan. I'm not quite sure why he really needed it. But anyway, I decided to put his data to good use. So here's my boy, and this is relatively normal. So this is the kid with the Cruzon. This is my so-called normal kid. I have now the 2 bones here, right? So for the first time, what you can do on the computer is, the pink is my boy, the silver is the boy with the Cruzon condition, right? So now I have some comparative data on the computer that I never could do before. Where do you put the pieces in space? And so here I'm moving these pieces, and 2 pieces just doesn't cut it, so you end up cutting into 3 different pieces. So we basically cut into 3 pieces: the forehead, the rim above the eyes, and then the mid-face, and move those into positions as a best fit. Becomes a cookbook. Go to the operating room, and I love this quote by Paul Tessie. Paradoxically, the osteotomy, which is pure mechanics, can be delegated to the assistant. They are always happy to cut bones and make noise with the power saw. So I never have a problem giving this to the residents to cut. The hard part is where do you put it? So these are, once again, guides here. Again, this is the forehead. The eyeballs are back below here for referencing. That's the side view. That's a jig. These are the plates that go into position. So you can see where we move the forehead and the mid-face. And so there he is before. There he is afterwards. So you can see the eyes haven't been moved, but the rest of the face is now in a better position here. And since my boy knew I was going to give this lecture, he went on and put a red shirt also on just for comparison. But you can see as a reference, you know, what we did. So again, another kid with Cruzon syndrome here. See the eyes are very proptotic. Same thing. In this case, we actually cut the face in half. We not only bring everything forward. These are the eyeballs. This is the brain here, you know, the dura. Everything's flipped over. This is a guide. This is how much bone we're going to take off the center here. And so this is after you split the face in half, bring everything forward here. You can see how much gap there is in terms of the advancement. And then that's the Lefort 1 segment, and here she is after 2 big operations. So again, and the orthodontist finished off the teeth for her in terms of that. So again, knowing, so all this sort of stuff really helps us to put pieces back together again. So in terms of the digital revolution, optimize morphology, optimize function, optimize the technical execution of the procedure here. I'll just speed this, just believe me, you can do this. More interesting is, how do you optimize skeletal fixation? Again, what we do is, when you put bone pieces together, what you're really doing is, you know, you have a gap here, and the residents are constantly bending plates back and forth, and these things will eventually snap unless you really get good at it. So instead of hand bending plates, we can now manufacture those plates, just like computer bumpers, right? Just like bumpers on BMWs, we can do the same sort of concept. We can actually design the plate itself and print it. So this is a custom plate. This is one off the shelf. And basically, that's a custom plate that we designed just like the front end assembly of the BMW here. And I don't want to go to the mechanical loads, the biomechanics of it. But how do you print something like this? So you have to know, you know, normally plates are made as a printing press. You print the metal and cut it into plates. But when you make something out of 3D, you have to use this complex machinery here, part of a patenting process here. But basically, plate goes in here, and what comes out, you know, this is a virtual plate from a computer design, goes in there, just like printing, and out comes a plate. So I can show you what the inside of this box looks like. You take an old RCA TV like this, turn it on its head, which none of you really have seen. This is basically an electron beam machine is what this really is, okay? You turn it on side, and since we just passed the 4th of July, you can make what's firecrackers. They're made from titanium powder. You can buy titanium powder off of eBay. and has a melting temperature of 1600 degrees centigrade. You know, the plates are made out of titanium. A lot of stuff we put is made out of titanium. Of course, this is not medical grade titanium, just to show you, but you can get the concept. So now, the only thing that can melt titanium at 1600 degrees is an electron beam. You can't just stick it in an oven, right? 1600 degrees centigrade is high. So you have to hit it with electron beams. How do you do it? This is what it looks like inside of here. This old cathode ray tubes from the old TV sets for people who can remember. The way you control the way you were able to see pictures, right? You had an electron beam that would go across, and these electromagnets would guide that beam. That's how pictures were transmitted back then. That's how you got pictures from the moon, for instance, when I was a little kid. So what you do is you find an old PC, and you design it, and you take the PC, then you hook it up to the magnets, and then basically you write the software to run it, and then eventually you get a real piece of titanium out of it. That's how those 3D plates were made. So now the impact efficiency in surgery is that this is Jason Souza, just finished was our chief in June, just finished, and the operating time was 45 minutes and 19 seconds, incision to closure. To put some scale to this, the typical operation, the average operative procedure for this is about 3 hours to do. He's doing this in 45 minutes. This is my chief resident. Because we do so much. We took 25 cases. Lafort went on incision to closure with the chief resident in May, because by that time they're good. You can just see the comparative, how much we progressed from 2006 to 2012 already here. Our operative times are so much faster now, and our outcomes are better. Once you have the CT, you can manipulate the world, opens up to specific, surgery specific for the patient. You can optimize anatomy, function, and surgery. And now to finish it off, how do you connect these dots? Okay? So I'll connect this pretty quickly. So in 1967, the first prototype CT scan was made, and by 1973, it became commercially available. Hounsfield was awarded the Nobel Prize in 79, and he was knighted, okay? So that's the first dot there to give you, 67. Also in the same year, 67, Paul Tessier showed us how to disassemble and reassemble the craniofacial skeleton with a remarkable series of cases. So 67 is the first thing that ties those two dots together. Now for the Beatles. Why did it take 2010 to get the records on iTunes? Anyone wonder why the Beatles tunes was never, when you never could get Beatles on iTunes? Anyone know? That's right. So the Beatles were making so much money. You remember the song Taxman, right? From George Harrison, right? They were making so much money. The accountants told them, you know what, you better do something with it. So they created a label called Apple Core. It was a record label. And so basically there was infringement in terms of Apple. And Apple agreed at that point in time, as long as the iTunes, as long as they wouldn't go into the music. But once they started iTunes, it became an issue to solve. Okay, so that's the first thing. There was entanglement. But the question is EMI. Beatles' record label was EMI, and Apple strike a deal on 20 cents. So they solved that dot. Question is EMI. All right, so what is EMI? EMI stands for Electric and Music Industries. So in 1962, they signed on the Beatles. EMI was then the parent company of the record label, right? EMI had so much money, they probably didn't know what to do with it at that point in time, right? Because the Beatles made so much money for EMI. Well, at EMI, there happened to be this guy named Hounsfield who had the idea of the CT scanner, and so some of that money clearly funded the CT scan. What happened was, apparently, Hounsfield had a research unit there, which nobody thought was going to go anywhere, but they had so much money, the CEO said, fine, redirected the money to the research end. So that actually helped fund the CT component of it. It's in the Lancet. Now for the finish. Great surgeons and great bands are outliers, right? They're out of any statistical group. And so what's common between Beatles, Tessier? Because without either Tessier or the Beatles and Hounsfield, virtual surgery really probably would be slightly different. It would have taken us longer to get there. So people have read Gladwell's book, The Outliers. If you haven't read it, it's really worth reading it. Beatles became the Beatles. Why? Because they practiced a lot, right? They put in 10,000 hours worth of work, practicing together. It's nothing like surgery. It's just the more you do, the better you get at it. And there's this great quote by Daniel Levitin from it: 10,000 hours of practice are required to achieve the level of mastery in anything. In study after study of composers, basketball players, fiction writers, concert pianists, chess players, master criminals, and what have you, this number comes up again and again and again, right? So what about surgery? This is a quote from Tessier. At what point does a caseload reach critical mass? Several major procedures a week as a minimum, and twice as many classical maxillofacial cases are needed. No activity means no experience, no safety, no progression. So consistent outcomes in surgery requires when do you get to 10,000 hours, right? As a surgeon. If you could put in 25 hours per week in the OR, 40 weeks per year, assuming you go for conferences like this, right? And you multiply, what's our X? X is roughly about 10 years. So it takes 10 years to become really comfortable as what you do as a surgeon, I think. So that's a background time. So can it have an impact on surgical resident training, right? We at least have the tools to help our residents to train. So this is Essie, as one of our residents. You know, I'm here as now training her, like I was going to train. Here's what the attending thinks, here's what the resident thinks. Nothing really ever changes, I think, right? Residents always think better than they are, right? Just like I did years ago. So after all, I think our residents grow up with video games. This is Clark Shirley, who was one of our chiefs who finished up and came back to join us. Clark is playing a video game, right? I never grew up with video games. And here he is doing another video game. It's the same thing. It's only natural for our residents to be able to simulate. This is my daughter. I actually give this to my daughter to do because she's faster at it on the computer than I am. You know, here's my daughter at 13 just sectioning the bones for me. I said, here, I want to cut it here and here, and she'll just do it for me, you know? So can virtual surgery planning make us a better surgeon? Can it really shift the bell curve, right? Can it make surgery more accurate? Can it make it more precise? Well, I think it can make it more precise, more accurate, perhaps. So I want to use this quote from "A fool with a tool is still a fool." When I worked at IBM, you know, I remember this quote very well. It's been used over and over again, but Grady Booch was the chief scientist there for that. So the way I think about it is, let me illustrate it this way, right? This is a fool with a tool who precisely and consistently puts it, but never puts it in the bullseye, right? This is simply a fool, has no idea where the target really is, right? And this is the gold standard. Somebody who really knows and trains themselves. Oh, look, I know where the target is. And using all the tools they can to retrain themselves to put them in. So, you know, the answer is, let's see. Can it really make us as good as Paul Tessier? The answer probably is not. I think some of surgeons are just clear outliers. What it can do is help us, like those like me who are in the back end of the curve, to be at the top end of the curve, to make it better. In terms of, I think there's a group of surgeons, a group of people who will still always be the outliers. This is Hugo Obegazer. I took him to the Apple store in 2008 when he came to visit me. Here he's 90 years of age, and he's got a computer case on his iPhone, and I just love this, but he doesn't need this at all. It's all hardwired in his brain, you know? This is Paul Tessier. I love this drawing. Look at this. These are all the surgical steps to the case, all listed out. Not on the computer, but on handwritten, on paper, on the side, you know, since to get cases like that. So here he is. He doesn't need any virtual planning to get results like that. So, but there is a future for the rest of us fools to be able to, with all the tools that we have. I owe acknowledgement. This is Michael Sarr from the Mayo Clinic, who I had a lot of great discussions as a young resident in training, and him as a young attending back then, of how to, not just about operating, but how to be a good surgeon, I think. And then, of course, these are my mentors, Paul Tessier training Henry Cotomo and Henry Cotomo training. So we all have lineages, right? We all have. Michael's lineage, I guess, was John Cameron, and he comes from the Halstead line, right? And we're here today because of our residents, above all. We're all here at academic institutions. We could all be someplace else in community hospitals and private practices and whatever, but we're really here because of the residents, because somebody taught us, and it's our duty to teach somebody else. That's it, thanks. Oh, and of course, homage to you.
Well, that was really an excellent lecture and a great way to start off our new year, because the challenge is to not have the goal to be mediocre. The challenge is to have the goal to be great, to be a master surgeon, and to use all the tools that we have to make us better. And what you all have that we didn't have is the amazing ability to have all of this sort of digitally enhanced part of surgery make you a better surgeon and make all of us a better surgeon. So I think with that, we will turn it over for a minute of questions. We're a little over time, but it really was just a fantastic introduction for our new year. Thank you
Thanks,
so much.
Dr. Farber. Any
Quick
questions?
question?
So I thought I knew how to do cleft lips and palates pretty good when I finished the training at the University of Illinois, and I just shared with you that 8 years later, I think I finally got it. So should we all continue to have mentors when we first finish? Because all these rare cases, clearly, we're all going to make a lot of mistakes. I don't want to go back and look at my first 200 cleft palates and see what the incidence of fistulas was there, because I'm sure it's much worse than the second 200 palates set of 200 palates that I did. How do we solve this problem?
A couple of things, right? If we go back to the UK model, United Kingdom, where they do clefts, right? Rare enough condition. They had about 11 centers doing cleft craniofacial work. They looked at it, since they fund them, right? They looked at the outcomes of this, and these are a beautiful series of papers in the 1990s in the Cleft Palate Craniofacial Journal where they looked at it. And what they found out was that the centers that had the highest volume of cases actually had the lowest complication rate because they're common, and they reduced it down to 4 centers. Interesting, that's from that perspective. But if you looked at it from the patient's perspective, they actually liked the centers that were not as busy because they had a better relationship with those surgeons. But in terms of outcomes, it was really better, so the more outcomes. So actually what it took for cleft lip and palate work, generally if you only did 6 cleft lips a year, right, which was about the average that they had found, it took about 20-some years to figure out what your real outcome was. So again, it's better to do such rare cases in concentrated areas. And then the next question is mentorship, right? I think we're at academic centers, and cases like this belong at academic centers. Where I'm at, I still, in the OR next to me is Mitch Grashevsky, who is now just turned 70 as a surgeon. You know, surgeons only get better as they get older, and it's just great to have your mentors right next to you. And one of the reasons I went back to Chicago was I really enjoyed with those who trained me, and I would be right with them in the OR next to me. And it makes such a world of difference to have good surgeons working with you.
It is lifelong learning,
Right,
no
yes.
question about it. Thank you again, and I think if anyone has further questions, we'll lean on Dr. Patel to be around in a few minutes to ask questions in the back. Thank you again.
Thanks,
Really
Al.
spectacular.